Hello all, welcome to the third video of this series. We'll begin with the first question. So the question says that a function is given by f of t is equal to sine square t plus cos 2t, then which of the following is true? Now I will solve this question in the time domain as well as in the frequency domain. So there will be two approaches for this question. The first one will be using the concepts in time domain, concepts of time domain. So given f of t is sine square of t plus cos 2t. We know that sine square of t is 1 minus cos 2t by 2 plus cos 2t. So this gives us 1 by 2 cos 2t. So we know that when we see f of t as a signal and not as a function, then we know that this is a DC component and this is a sinusoid component. Okay, and this is of the form cos omega naught t. So it should say that since this is a DC component, I have already mentioned in the previous video that DC component corresponds to a frequency at 0 hertz or based on the units. Okay, so 1 by 2 is just the amplitude, but frequency wise it means a component at f is equals to 0. And considering cos 2t, we know that omega naught is equals to 2, and that is to say 2 pi f naught, where f naught represents the frequency of the given sinusoidal signal. F naught is 1 by pi hertz. So the given signal has frequency at 0 and 1 by pi hertz. So the option is B. Now this was using the time domain. Now suppose, let's say, if you found this question in the exam and unfortunately you didn't get to you didn't know how to express this, but you know how to write the frequency domain equivalent of the signal. So we'll try to solve this using the frequency domain approach. Now f of t is given by again 1 by 2 plus 1 by 2 cos 2t. Okay, now we know that this signal is also periodic, and by periodic we can say that we can express this using the Fourier coefficients. Okay, and again we already know that this represents a DC component. This represents frequency at f equals to 0 hertz. So we'll just concentrate on the second sinusoidal component, how to express when a specific signal is given, how do you express this in terms of the Fourier coefficients. So n equals minus infinity to infinity Cn e power j omega naught nt for half cos 2t. That is to say, what will be the Fourier coefficient and the complex exponential multiplication factor for this symbol, that for this signal. Okay, now instead of writing as f of t, I will take this as f cap of t just to avoid the confusion. Okay, we can write cos 2t as e power j 2t plus e power minus j 2t divided by 2, and e power j 2t plus 1 by 4 e power minus j 2t. Now if you compare this equation, let's call this as equation 2 and let's call this as equation 1. If you compare this with the first equation, then you get to know that 2t is nothing but omega naught nt. Now one might ask, what is the value of n? There is a shortcut, or maybe you can say one more concept in this. N will represent the number of Fourier coefficients. So for this example, that is for half cos 2t, we already know that cos 2t has only one frequency component, right? It has only one frequency component. It should say that n should be 1 for this, because there is only one frequency component. So n will be 1 here, and 2t is omega naught t, and omega naught will be 2. So again with the same approach, 2 pi f naught is 2, so f naught will give us 1 by pi hertz. So, and we already know that there is one more frequency component at 0 hertz. That should give us the answer as B again. So we solved the same question using the time domain approach and using the frequency domain approach. Now the emphasis on this question is the time domain. We can already solve it using the basic trigonometry that we know, but in the frequency domain we got to know how the given signal can be expressed in terms of its Fourier series coefficients, and taking any sinusoidal component, we came to know that it has only one frequency component, and therefore n should be 1 for this. I guess most of you did not know about this. And not just this, finally we also got the solution for our answer. So that's why I have been telling, solving more questions will give us more concepts rather than reading the same concepts again and again. Okay, let's jump to the next question for this video, and this will be the last question for this video. The question says that let x of t be a continuous time periodic signal with fundamental period of 1 seconds. Let ak be the complex Fourier series coefficients of x of t, where k is integer valued. Then consider the following statements about x of 3t. The complex Fourier series coefficients of x of 3t are ak, where k is integer valued. The complex Fourier series coefficients of x of 3t is 3 times ak, where k is integer valued. Then the fundamental angular frequency of x of 3t is 6 pi radians per second. Okay. So how do we begin with this solution? Given that x of t is periodic, so again the signal is periodic, and we can represent x of t in terms of its Fourier series coefficients. But here the Fourier series coefficient is also mentioned, so x of t will be k. And if we represent this in the standard Fourier series convention, they are asking us what is the Fourier series coefficient for a signal which is scaled by 3 times in the time domain. What will be the Fourier series coefficient for this? So now let's write the Fourier series coefficient using the same basic formula. So this is our basic formula, and we can tweak this as per our needs. So x of 3t, we are just replacing t by 3t. Okay, so this should give us cn, or anything is fine. I'll just rub it to avoid confusion. Let's write it in terms of k itself. ak e power j omega naught k into 3 times t. Okay, so let me explain one more concept in the Fourier series equation. Just change the color to n is equal to minus infinity to infinity Cn e power j omega naught nt. So whenever we see this equation, first we should know that omega naught represents the frequency term and also the time term. Time term in the sense the time period, and frequency the definition as we know. Okay, so omega naught, if we consider in the frequency domain, then we talk about its frequency, that is the fundamental frequency or the angular frequency. If we consider it in the time domain, then we consider the fundamental time period. Okay, so then comes the term Cn, that is to say x of t is a weighted complex harmonic conjugate. Okay, x of t is a summation of weightage of complex harmonic exponential. That is to say, for a value of n, this will be the corresponding coefficient. So suppose let's take a signal x of t having two Fourier coefficients. Okay, so c1 e power j omega naught into 1 into t j omega naught into 2 into t. Okay, now as you can observe, this coefficient, Fourier series coefficient, corresponds to a change in only n, not in the value of omega naught or not in the value of t. Similarly, c2 corresponds to the change in n, not in terms of t. So that should say whenever we change n, that should change our Cn, or it only affects the frequency Fourier coefficient. It is not affecting anything in our time domain signal. And coming to the next concept, if we consider t, let me change the color. If we consider t, then that affects our time domain signal. Okay, so if we change t as alpha t, then our x of t changes as x of alpha t. Okay, so if we use this in our present question, x of 3t is k minus infinity to infinity ak e power j omega naught k into 3t. So as I have explained, if we are changing t, then it only changes the value in the time domain, that is not affecting our Fourier series coefficient. So that is to say, x of 3t will also have a Fourier series coefficient of x of ak, which is the same as x of t, and that should tell that the statement 1 is true. Obviously the statement 2 cannot be true, because the Fourier series will not be changing even if we scale our time domain signal. Now again, as I have told, omega naught, when we change omega naught in the frequency domain, the frequency changes, and in the time domain the time period changes. Or in other words, let's write the same equation. X of t ak e power j omega naught k t. Now again we are slightly modifying the equation. X of 3t is k is equal to minus infinity to infinity ak k into 3t. Now instead of writing this, I will modify this complex exponential as e power j into 3 omega naught k into t. Okay, so what should this tell me? If we compare this with our normal equation x of t j omega naught kt, let us represent this as omega naught omega dash maybe, because they are asking us the fundamental angular frequency. Okay, the fundamental angular frequency of x of 3t. So this term is our sorry this term is our new omega dash. So omega dash is 3 times omega naught, right? So this is 3 times 2 pi by t naught, and t naught is given 1, so this should give us 6 pi radians per second. So in this question, instead of just solving, we got to know how the Fourier series coefficient can be written for a particular time domain signal, how the value of n affects the time domain property or the frequency domain property with Cn and relation between Cn and n, and how the value of t affects the time scaling in the time domain. And also we came to know that omega naught affects both the frequency and also the time domain behavior. So the final answer for this question is 1 should be correct and 3 should be correct. So the correct option for this question is B. So we have covered again 2 more questions in this video, and probably in the next video we'll be covering 3 questions, and so on. We'll keep on increasing the number for every 2 videos, so it becomes comfortable for all of us. I hope you have learnt in these the first 3 videos. So if you have anything, or if you get any doubt in at any part or at any instant in this video or any other video, feel free to comment, and maybe I can help you out. So I'll see you in the next video. Thank you.